এখানে দাও তুমি একটু A very good afternoon to one and all present here. I am Suyesh Agarwal on behalf of Allen House Public School Khalasiland Kanpur. Welcome you all to Mathematica. I would like to welcome Aparna Mukherjee who has been a judge for the day. This activity-based competition is a game of mind, intellectuality, interest, power and joy. Mathematics is the basis of everyday life. We need to calculate not only how much energy we spend in a day, but how much we preserve it. The modern era is the era of calculations. We have calculations in probably every aspect of life, and we learn from each one. Pythagoras once said that there is geometry in the humming of strings and there is music in the spacing of the spares. Pure mathematics is in its own way the poetry of logical ideas. It makes us more alert, more involved, and more aware. It also increases the analytic ability of our minds. I would like to congratulate the teams who have made to the second round of the competition. I would like to make everyone aware of the rules of round 2. The activity must be based on the topic allotted. The time limit for conducting the activity will be maximum 10 minutes, including the settings of the activity. The video of only the school performing has to be switched on during the activity. All the others will keep their videos off and mic muted. Once your round is over, switch off your cameras and mics. Use of any form of search engine or hard copy or soft copy is prohibited. Participants must have a stable network connection. Video freezing and camera switched off will lead to negative marking. Follow the rules properly, otherwise it will lead to disqualification. The judge's decision will be final. The criteria on which the judges would judge the competition are as follows: topic covered, explanation, creativity, presentation, and time limit. Now I request school code M02 for their activity. I repeat M02 for their activity.
M02 is not here, so we can proceed to the next code, M04.
Yes. Leave for the moment. Good afternoon, everyone. Today I, Mansi Verma and Aparna Shankar of School Code M04 are here. As you all know, that the relation between biology and mathematics has a lot of scope in coming future, and any link that connects to them becomes significant. Here's a question of biology that states, why are the cells in an organism so small and not large in size? The answer to this question has as much to do with mathematics as biology, since it involves the basic concepts of surface areas and volumes of three-dimensional figures. Here, we are going to explain you the comparison between the ratios of surface areas and volumes of the cell when it increases in size. For that, let's imagine that the cell is a cube. Now let us move on to Aparna, who is going to demonstrate to us the relation between the surface areas and volumes of the cell. Thank you, Mansi. Now, as we know, now before we get into the mathematical demonstration, let us first understand what a cell actually is. A cell is a basic structural and functional unit of life. For over here, you can see that organisms can be broadly classified into two types: unicellular and multicellular organisms. Unicellular organisms are made up of only one cell, whereas multicellular organisms are made up of more than one cell. Now, in the human body, the average size of a cell is estimated to be about 10 to 20 micrometers in size, and there are more than 30 trillion cells in our body. But have you ever wondered why cells are so small in size? Well, the answer to this lies not only in the field of biology but also in mathematics. Therefore, today we are going to demonstrate in front of you all the mathematical explanation of why cells are so small in size. For this, let us first assume the cells to be cubes. As you can see over here, we have a smaller cube and a larger cube. The dimensions of the smaller cube are 5 into 5 into 5 centimeters, and the dimensions of the larger cube are 7 into 7 into 7 centimeters. Now, as we know, the total surface area of a cube is 6 into the side squared. Therefore, the TSA of the smaller cube becomes 150 centimeters squared, and the TSA of the larger cube becomes 294 centimeters squared. The volume of a cube is side cube. Therefore, the volume of the smaller cube becomes 125 centimeter cube, and the volume of the larger cube becomes 343 centimeter cube. Now that we have found out the TSA and volumes of these two cubes, let us find the TSA to volume ratio of these two cubes. The ratio of the smaller cube is 150 upon 125, which on simplifying will be 6 is to 5, and the ratio of the larger cube is 6 is to 7. 6 is to 5 is clearly larger than 6 is to 7. Therefore, it is evident that the smaller cube has more surface area per unit volume ratio as compared to the larger cube. Now let us move on to Mansi, who is going to conclude the activity with a few interesting facts. Now consider these cubes to be actual living cells that need oxygen and nutrients to survive and reproduce. For the entire cells to receive oxygen, oxygen diffuses through the cell membrane. Since the smallest cell has larger surface area relative to the larger cell, the oxygen diffusion rate is higher. Therefore, oxygen diffusion rate is higher, and oxygen diffusion rate is higher. Therefore, oxygen diffusion rate is higher. Therefore, oxygen diffusion rate is higher.
Participant, you're not clear. Your video is paused.
School code M04, your video is paused. I think there is some network connection issue at the end of M04. Let's call the another participant, Suyash.
Coming up next is school code
What is this?
M05 with the performance.
Good afternoon,
Excuse me.
everyone.
M04 has already performed. We just performed our activity right now.
Yeah, you did, but actually your video was frozen.
The video was frozen, ma'am.
Yes, child, the video was frozen.
Ma'am, at
We'll
what
call
part
you
did
at
it?
the just a second, child. We'll call you at the last again. Okay, we are continuing with M05. We'll call you at the last again.
Okay, ma'am.
Good afternoon, everyone. I'm Abhishar Yadav, and our school code is M05. So, have you ever thought that what is the maximum length of the phone which can be fitted in your room? Yes, it can be calculated by calculating the diagonal of your room. So, today's activity is the verification of the diagonals of the cuboid. So, my friend Simran Yadav will demonstrate the activity. On to Simran.
You are muted. Please.
Now I will show it practically.
And then pin my.
I request everyone to please pin my video. The length of it is 26.1 centimeters. We'll approximately take it as 26 centimeters. The breadth of it is 21 centimeters. Height of it is 6 centimeters. This is a cuboid. Now let's square the length, breadth and height. We know the formula under root L square plus breadth square plus height square. So it goes like this. Under root 676 plus 441 plus 36, which will come under root 1153, which will 33.9. Now we'll take it as approximately 34, as here we have taken 26.1 to 26. So here we can take 33.9 to 34. Yes, this is really equal to. Now let's measure it. Yes, this is exactly 36. 30. Thank you.
Well done, M05. Now I request M06 to present their activity.
Greetings, esteemed judges and my dear friends. Today, I, Arnav Gupta of class 9th and
Setia of class 10th
of Allen House Public School Ghaziabad, school code M06, are going to demonstrate an activity on the topic solids, three-dimensional figures, to verify the surface area of a sphere. Before we start the activity, the materials required for the activity are a ball that will represent our spherical object,
This is the ball,
cardboard,
cardboard,
glue,
glue,
scissors,
scissors,
compass,
compass,
ruler,
a ruler,
pencil,
pencil,
string.
pins.
We know that the total surface area of a sphere is 4 pi r square. Now, to demonstrate the activity, over to Pihu Didi.
Thank you, Arnav. To find the total surface area of the sphere, we need to find the diameter as well as the radius of the sphere. So, to find the radius as well as the diameter of the sphere, we need to take two cardboards of equal length and size. Place the ball at the table and keep this cardboard parallel to the sphere. Now, if we will observe carefully, the distance between the edges of these two cardboards is equal to the diameter of the sphere. So, I've already made another model for you all to understand that how we can find the diameter of this sphere more clearly. Here's the model. If you will look carefully, you can find that I have pasted these two parallel cardboards with this base, and this is the spherical ball that I have taken earlier. Now, if you will observe that the distance between the edges of these two cardboard is equal to 7 centimeter. So this will prove that the distance between the cardboard is equal to the diameter of the sphere. So the diameter of the sphere has comes to be 7 centimeter. And as we know that the radius of a diameter is equal to the half of the diameter, we will simply divide the diameter by 2. So the radius of this sphere will comes to be 3.5 centimeter. Now, as we have found the diameter as well as the radius of the sphere, now let's have a practical activity to find the total surface area of the sphere. For this, take a spherical ball and a board pin. Now place a board pin at any point of this sphere as I have done. Next, take a thread and tie a knot at the top of the sphere. Cut down the extra part. Now take the Fevicol and apply some amount of Fevicol all around this pin as I have done. Now roll this thread all around this pin very slowly so that no space or gap can be seen between these threads. As you can see, I have tried not to leave any space between the threads. Now, I have already prepared another model for you to understand that how it will look like after we have completed the ball with all the thread. So this is how it will look after we will cover the whole ball with the thread. Now, for the next step, take another pin and just try to unwrap the thread that you have covered all around the ball. Now, we will use this thread later, but before using the thread, take a plain cardboard, a compass, and a scale. Now measure 3.5 at your scale and draw a circle of the same radius on the cardboard. I have drawn only one, but you need to draw 4 of the similar shape. Now, take some glue, fix a pin at the center of this circle. If it is not fixing, just leave it. And add some glue at the center of this sphere. Or we can say a circle made out of the sphere that we have used earlier. As this is a thread, now try to wrap this untied thread all around the circle so that it can cover the whole area of a circle. I have done a bit for you. But if we will complete this activity with 4 other circles also, this is how it will somewhat look like when we will paste the untied thread of the sphere that I have taken earlier at the same on 4 circles of the same radius, which is equals to 3.5 centimeter. Now I will request Arnav to explain the observation and the conclusion of the activity that I have shown.
Didi. We will observe that the thread will finish unwrapping when the 4 circles are filled by the thread, as the area of one circle is equal to pi r square. So the surface area of a sphere is 4 pi r square, which means 4 times the area of one circle. This is how we can find the total surface area of a sphere, which is 4 pi r square. Thank you all.
Thank you.
That was a good effort, M06. Now, I request M07 to perform their activity.
Hello everyone, this is Mayuk Das from school code M07. Today, we discuss about the topic solids, that is the 3 dimension. Now, before entering into some things that we will discuss in our activity, let us know some basic things about 3 dimension. Everything that we see around us are in 3 dimension, but the paper which we write, where we draw, is a 2 dimensional space, that is a Cartesian coordinate system. Now, we have a lot of things around us which are solids, 3 dimensional. For example, this can be termed as a cylinder. This is a cuboid, and I have a ball, which is a sphere. Now, if we try to draw a cuboid on a paper, we will see that if we draw a cuboid, it seems to be a cuboid. But if we make this on a plane, these planes have their own coordinates, and we can say these are xy, pq, etc. Everyone will think that I have drawn the figure is a cuboid, but no, it is not a cuboid. It is not a 3 dimensional figure because the points which are on the cuboid are on the 2 dimensional plane, so it's not a cuboid. Now, we can convert various 2 dimensional figures into 3 dimension. For example, if we take a right angle triangle and revolve it around its axis, that is, its height, we will get a cone like this. With the base of the right angle triangle with its radius and its height as a perpendicular. Now, if we take a rectangular piece of paper and roll it, then This is my rectangular piece of paper. I have rolled it. It looks like a cylinder. So I've converted two-dimensional figures into three-dimension. Now I will request my partner Priyanshu Guin to explain one of his activity.
Good afternoon, everyone. So today I was going to explain the area of a sphere, but coincidentally M06 has explained the same thing. So in last moment I have planned something different. Like if you take a ball and you want to find out its area, then you may do the same thing, but we are performing a different activity. You take strips and just cut it. Like I am taking this strip and now I am rolling over it. So you are taking n number of strips and you are cutting here. But unfortunately, all their diameters are not same. So we are taking this sphere and then we are cutting it into strips like this. So let's find out the area of the hemisphere. So we have taken the strips. Let's assume this strip as this substance, and you know this thing is same for all. So you are taking n number of strips and cutting it from here, and you are taking it out. So this will be in the form of rectangles like x, and this length will be 2 pi r, 2 pi, and take the radius as a1. As you move from top to bottom, you will experience that all the radius will change. Now the area of every strip will be 2 pi a1 into x till n number of strips. So 2 pi a2 into x, an into x, I'm sorry. So for all of them, it will be 2 pi x common and a1 plus a2 plus a3, like this, a n. Now this x, where does this come from? Hello, am I audible? Hello?
Yes, you're
Hello.
audible.
Thank you.
Yeah, you're audible.
Now if you take like this and this x, and you are dividing into n number of strips, so this x will be
Participant, your video is off. I repeat, participant, your video is off. Participant, your video is off.
Sorry, my net was gone. Sorry for the inconvenience. Like, see, check this A1. We are taking this as A1. So this A1, as you have, if you have studied trigonometry, then you may identify this. See, this is A1. This is the radius, R. So this length, A1, we can write A1 as R sine alpha. If we take this as alpha. So like this, we can write all the A's as R sine alpha plus R sine 2 alpha, R sine n alpha. Then R common, sine alpha plus sine 2 alpha. This x shall be 2 pi alpha into R, and then 2 pi R square alpha into sine n alpha. If you have studied integration, then you can find out this value, as this value shall be equal to 1 by alpha. So alpha and alpha will be cancelling, and the equation will be 2 pi R square. And keep it in mind that we were calculating the area of hemisphere. So the area of the sphere will be 4 pi R square. But without using integration, you can find out this thing also. Like, you can check it manually. If you are taking n number of strips, let us assume n as 10. So the formula is 2 pi R square alpha into sine alpha sine n alpha. Like this, you can check that this is equal to 1. I mean, this is not equal to 1. This is equal to 1 by alpha. So after this, we can state this is equal to 2 pi R square. Hence, the formula is 4 pi R square. Thank you.
Well tried, M07. Now I request M11 to perform their activity.
Shastranam Gaditam Nishchitam. This means that the basics of math should always be clear. Good evening to each one of you. This is Rashika Agarwal and this is Shubhra Verma, representing M11 under Group C. We are privileged to be here again. That's true. In the beginning, from Vishnu is worthy of interpretation. So, before switching out with this wide world of mathematics, we should focus on the basics first. The objects that have definite shape and definite size are known as solids. Solids have three dimensions. That's why they're also called three-dimensional or 3D shape. Solids have faces, edges, and vertices. Cubes, cuboids, spheres, etc. are 3D figures. Now, let's differentiate between 2D and 3D figures. Consider this example. Imagine that three lines are meeting each other, making an angle of 90 degrees with their adjacent sides. So the sum of the angles here will be 270. But this contradicts the fact that the sum of angles around the points on the plane is 350. Now each one of you, please give a glance to the corner of your view. There you Now let's move on to 3D. This is a rectangle. The area of rectangle is length into breadth. Now if we fold this rectangle along its length, then the length of the rectangle becomes the circumference of the base of the cylinder and the breadth of the rectangle becomes the height of the cylinder. So the curved surface area of the cylinder becomes 2 pi rx. Let's consider another example. This is a cone. One basic thing about the cone is it is usually written as right circular cone. Now what students usually don't know is why do we call cones right circular cone? So let me explain it today. You can see that this is the height of the cone and this is the radius of the cone. These two are making an angle of 90 degrees. And this is why cones are also called right circular cone. This is the slant height, as you can see, it's slant. That's why it's called slant height, and it's represented by L. This right angle triangle, this triangle is the right angle triangle, and it satisfies the Pythagoras theorem. This is a sphere. The curved surface area and the total surface area of a sphere are 4 pi r square, and the volume of sphere is 4 by 3 pi r cube. Now suppose if I cut this sphere into two parts, then I will be getting two hemispheres. Now this is an hemisphere. The curved surface area and the volume will be divided, but the total surface area will not be divided because here we have got a new surface appear on the top. So the total surface area of this hemisphere will be the curved surface area plus the area of this juicy part. So the total surface area of hemisphere becomes 2 pi r square plus pi r square, that is 3 pi r square. Now, in practical life, we usually see combination of objects, that is combination of solids. One example is this lamppost. This lamppost is a combination of a cone and a cylinder. If we want to take this lamppost, then we will be needing the curved surface area of the cylinder, the area of the ring, and the curved surface area of the cone. Now suppose if this lamppost was made of wood, then the volume of the lamppost will be the volume of the cylinder plus the volume of the cone. Rashika, if this was a toy rocket, then what will there be any difference in the total surface area which is to be painted? Yes, there will be a difference. If it is a toy and you want to paint it, then the total surface area will require the area of the base, the curved surface area of the cylinder, the area of the ring, and the curved surface area of the cone. Now there is one more example. This is a pressure. As you can see, it is a combination of a cuboid and a semi-cylinder. The semi-cylinder can be understood by this thing. This is the cucumber. It is cylindrical in shape. When it is vertically divided, we get a semi-cylinder. And as you can see, this shape is similar to this. Now, if you want to calculate the volume of this figure, then we have to simply add up the volume of this cuboid and half the volume of cylinder because this is a semi-cylinder. Now, students, if I want to cover this treasure box with a beautiful cover sheet, what area will be required? Then you will require the total surface area of it. The total surface area of this treasure box will be the area of these four walls, the area of the base, the incurved surface area of this part, and the area of these two cylinders. Let's make it clear with one more example. Here I have another combination of solids. In this, the solid combination is of a cylinder and two spheres. Another notable situation is the distribution of volume into consequent smaller parts. For example, this is a cylindrical glass and it has color water in it. For example, if we want to pour this liquid into a spherical bowl similar to this, suppose we need 50 hemispherical bowls to empty out this glass. Then the volume of this liquid in the cylindrical glass will be equal to the volume of liquid that we have poured in those 50 hemispherical bowls. And there are plenty of more examples. As you can see, one such example, if it is a log of wood and two hemispherical cavities are cut out at the two ends of this log, then the volume of this log will be increased because we are taking out the quantity of wood, and the total surface area will be increased as curved surface of cylinder plus thus the surface area of the two hemispherical cavities. And one more example, this is a cloud. It is also a combination of solid. It has a cylinder on top and a sphere at the bottom. And the spheroid is cylindrical here and spherical in the bottom. What needs to be noted here is the radius of the cylinder coincides with the radius of the cone. That is, the radius of the cylinder and the cone is equal. But in this example, the radius of the spherical curve was greater than the radius of the cylindrical curve. One extremely practical example is the missile launch pad. You can see that the launch pad is a cuboidal base, cylindrical rocket, and a conical lens. This is also an example of a combination of solids. Rashtra, children used to say that volume and surface area of solids is a subchapter. Yes, but after seeing these 3D objects, I can say that it is a practical and interesting chapter. Math is a practical subject. We can learn it by doing. We don't need to memorize anything. Math is not a problem to be solved, but a number to bring to it. Thank you.
Well demonstrated M11. Now I request M16 to perform their activity. I request M16 to perform their activity.
Good evening, everybody. This is Balirani. And I am Kushagar Gupta. We are students of school code M16. Today, we are going to give a live demonstration to take out the formula for the surface area of a sphere. Talking about spheres, sphere is an object in a three-dimensional plane from it is a collection of a set of points equidistant from a center. The central point is the center of the sphere, and the distance, which is equivalent for all the points on the sphere, is the radius of the sphere. A sphere is a 3D object that is irregular in nature. There are a multitude of life examples of sphere that we can see all around us in our daily lives. Whether we talk about heavenly bodies like Earth and Moon, a globe, fruits like oranges, or sports ball. Spheres can be seen all around us. So now, let us demonstrate an activity to take out the surface area of a sphere. For that activity, we are going to require some material.
The materials required for this activity are a spherical ball, some glue, a thread, a pair of scissors, a marker, a ruler, a compass and a pencil, and some cardboard and an A4 sheet.
Now that we have all the material required, let us commence with the activity. For that, we are going to first take a spherical ball. This is going to be the representation of a sphere for us to do. First, we are going to measure the radius of the spherical ball. For that, we have prepared an erect cardboard setup. We are going to place the spherical ball between two erect pieces of cardboard such that the ball is snugly fit between these two pieces. Since the sphere is touching both the edges of the cardboard, the distance between the two cardboard gives us the diameter of the sphere. Now let us figure out the radius.
On measuring the distance between the two cardboard sheets, we find that the diameter of the spherical ball comes out to be 6 centimeters. On dividing the diameter of the spherical ball by 2, we obtain the radius of the spherical ball, which is equal to 3 centimeters.
Now that we have successfully obtained the radius of the spherical ball, let us move on to the surface area. For that, we are going to take our spherical ball and then, with the help of a nail, we are going to pierce the ball. Then we are going to take our thread and tie one end of the thread to the head of the nail, and then we are going to carefully wind the thread onto the spherical ball, covering all the surface area of the sphere, ensuring that there is no gap between the windings.
Like this, we'll continue to rotate the thread all around the spherical ball until the spherical ball is entirely covered with the thread. And in order to avoid any wastage of time, we have already prepared a ball which is fully wrapped with the thread in advance.
Now that we have covered our ball with the thread and obtained the structure, we are going to take our A4 sheet. Now we are going to draw 4 contour circles having radius 3 centimeter that is equal to the radius of the sphere as we figured out earlier. Taking a radius of 3 centimeter from the ruler on the pair of compass, we are going to draw the 4 circles. As you can clearly see, we have already drawn 3 circles and now my classmate is drawing the 4th circle. Now that we have drawn the 4 circles onto the sheet of the paper, we are going to take a spherical ball around which we had moved the thread. Now we are going to take the thread and unwind it carefully. We are going to unwind the thread and remove the nail from the spherical ball. Now we have obtained the whole length of the thread. This whole length we are going to divide into 4 equal segments. We have done so in advance and prepared 4 equal segments from this thread that we have covered the ball with. As you can see, we have 4 segments. Now, we are going to paste these segments onto the sheet of paper. We are going to take one of the segments of the thread and carefully, with the help of some glue, we are going to paste this onto the circle that we had drawn onto the A4 sheet. As you can see, Kushagra is coiling this thread onto the circle. We have to be very careful that the thread covers all the surface area of the circle and is snugly bound. It should be coiled such that no area of the circle is left uncovered. As you can see, I'm covering the other 4 circles with the help of some glue so that we may paste the segments of thread onto the circles.
We have already prepared 3 circles of the other 3 threads in advance.
Now we are going to paste these segments onto the A4 sheet. On unwinding this thread from the spherical ball and pasting it onto these circles, we observe that all the length of thread that was used in covering the spherical ball got used up in covering the area of 4 circles having radius equal to that of the spherical ball. That is, the surface area of a sphere is numerically equal to 4 times the surface area of 4 circles having radius same to that of the sphere. That is, the surface area of a sphere is equal to exactly 4 times the area of circles having radius same as that of sphere. That is, surface area is equal to 4 pi r square. We hope we were clear with our demonstration. Thank you for being such a patient audience. Thank you.
Thank you.
What an enthusiastic performance! Now, I would like to call upon School Code M18 for their performance.
Just 1 second. My badge fell down. Just 1 minute. Um, good afternoon. I'm Matthew Mishra.
Good afternoon. I'm Vasvi Singh.
Our school code is M18, and the topic given to us is 3D solid figures, 3D shapes. And the mathematical concept chosen by us is the Euler's law. Leonhard Euler was a Swiss mathematician, physicist, astronomer, geographer, logician, and engineer. He was one of the greatest mathematicians of the 18th century and is held to be the greatest in history. He made important discoveries in the various branches of mathematics and devised laws for the same. One of his most famous laws is the Euler's law of 3D shapes. A 3D shape is a three-dimensional figure that has three dimensions: a length, a breadth, and a height. A 3D shape consists of flat surfaces called faces, the place where two faces meet called the edge, and the vertex, that is the place where two edges meet. Now, my friend Vasvi will. According to Euler's law, the number of faces in a 3D shape, that is F, plus the number of vertices, that is V, is equal to 2 more than the number of edges, that is E. In common terms, we define the Euler's law as F plus V equals to 2 plus E. Now my friend Vasvi is going to demonstrate the Euler's law with the help of some activity.
So now we'll verify the Euler's law with the help of an activity. So the materials required for the activity are, we have taken a few 3D shapes. So the first shape that I've taken is a square pyramid. Now we all know how a square pyramid looks like, right? It has 1, 2, 3, and 4 triangular faces and a square base. So in order to apply the Euler's law, we first need to count the number of faces, vertices, and edges in a square pyramid. So let us start counting. It has 1, 2, 3, and 4 triangular faces and a square base, which makes a total of 5. So it has 5 faces in total. We have 1 vertex at the top and 4 vertices at the base. So it gives us a total of 5 vertices. Now let us count the number of edges. It has 1, 2, 3, and 4 slanting edges and 4 edges at the base. So which gives us a total of 8 edges. Now the Euler's law states that the number of faces, that is 5, plus the number of vertices, that is also 5. So we get the left hand side of the equation as 10. Now the right hand side of the equation says that the number of edges, that is, we've got 8 plus 2 gives us 10. Since the right hand side of the equation is equal to the left hand side of the equation, we can say that Euler's law is applicable in a square pyramid. Now let us take another figure. Here I've taken a triangular prism. So a triangular prism has 2 identical and parallel triangular faces and 3 rectangular faces in between. So now let us count the number of faces, edges, and vertices in a triangular prism. Let us start. It has 1 and 2 triangular faces and 1, 2, and 3 rectangular faces in between. So we get a total of 5 faces. Now let us count the number of vertices. It has 1, 2, 3 vertices at the first end and 1, 2, and 3 vertices at the other end. So we get a total of 6 vertices. Now let us count the number of edges. It has 1, 2, 3 vertices, 3 edges here, 1, 2, and 3 edges in between, and 1, 2, and 3 edges at the other end. So we get a total of 9 edges. Now the Euler's law states that the number of faces, that is 5, plus the number of vertices, that is 6. That is, we get a sum of 11 on our left hand side. The right hand side says that the number of edges, that is 9, plus 2, we get 11. Since our right hand side is equal to the left hand side, we can say that the Euler's law is applicable for a triangular prism as well. Now over to Mathri.
Now I'll verify the Euler's law with example of a cube. A cube is a 3D solid figure which has 6 similar square faces: 1, 2, 3, 4, 5, and 6. It has 1, 2, 3, 4 edges at the top, similar 4 edges at the bottom, and 4 vertical edges. The number of vertices in a cube are 1, 2, 3, and 4 at the top, and 1, 2, 3, 4 at the bottom. So we got 6 faces, 12 edges, and 8 vertices. Now let's apply the Euler's law to this figure, to this solid shape. On applying the Euler's law, we first add the faces, that is 6, to the vertices, that is 8, so we get 14. It should be equal to the number of edges plus 2, that is 12 plus 2, which gives us 14. Now, since the right-hand side equals to the left-hand side, which is 12, which is 14, we can say that the Euler's law is applicable to this cube as well. So with these examples, we can understand that the Euler's law, that is F plus V equals to E plus 2, is applicable to all 3D solid shapes. Thank you.
A well-presented activity, M18. Let's move ahead. I request M19 to present their activity.
Myself Ayushi from class 9th with my school code M19A is here to wish all of you a very good evening. So today I'm damn sure that you all might be aware of the solids, which are a three-dimensional figure or objects or shapes. So today I will be performing an activity, not the activity based on the serious concepts or the very complicated concepts which you all might think which are boring, like the surface areas, volumes, etc. and etc. I will be taking a very simplest concept, that is, what are the 3D figures or three-dimensional figures. So let's begin. So I hope you all might be able to see my screen. So here you can see that the three objects are kept here. This is a cube, this is a rectangular pyramid, and this is a triangular prism. So a common thing in all these objects is that all these objects are 3D figures, means three-dimensional figures. So first of all, let us understand what is a 3D figure. In geometry, a three-dimensional shape can be defined as a solid figure or an object or shape that has 3 dimensions, that are length, width, and height. Unlike the two-dimensional shapes, three-dimensional shapes have thickness or depth. So here in all these three objects, you can see or found the 3 dimensions. First of all, let us take this cube. In this cube, you can find the 3 dimensions. What are they? The length, the breadth, and the height. And here also, the length, the breadth, and the height. In this object also, length, breadth, and height. So now, first of all, let us talk about the cube first of all. Now, let us remove these two objects for few moments. Now, what is a cube now? It is a three-dimensional figure, we know that. But what is exactly a cube? A cube is a three-dimensional solid object bounded by 6 square faces with 3 meeting at each vertex. The cube is the only regular hexahedron and is one of the 5 platonic solids. It has 6 faces, 12 edges, and 8 vertices. Now, what are the faces, edges, and vertices? No need to worry. Simply, the faces are those areas or those regions of any object that are bounded by the boundaries or the edges of an object. Then comes to the edges. Edges are nothing. These are the sides or the boundaries of a given object. And at last comes the vertices. Vertices are nothing. These are the corners or the points or point of intersection of two edges. Now let us understand in this cube that where are the faces, edges and vertices. So in this cube you can find that this is a face number 1. Here you can find face 2. Here you can find the face 3, face 4, face 5, and at last comes the face 6. So here you see that these are all faces of this cube. So here we can conclude that, and we have proved that a cube has 6 faces. Now let's talk about the edges. How many edges does a cube have? Let's see now. One boundary or one side or one edge. 1, 2, 3, and 4. 4 edges, then 5, likewise 6, then 7, then 8. Now 9, 10, 11, and 12. So here we also conclude that it has 6 faces and 12 edges. Now last but not the least comes the vertices, means the corners or the point of intersection of two edges. So 1, 2, 3, 4, and likewise comes 6, 7, 8, and 9. Now let's move on to another object. Let's take an example of another object, which is a 3D figure. So that is none other than a triangular prism. So what is a triangular prism? So before understanding about a triangular prism, we should understand that what does prism mean? A prism is a three-dimensional shape with two identical shapes facing each other. These identical shapes are called the bases. The bases can be triangle, square, rectangle, or any other polygon. Other faces of a prism are parallelograms or rectangles. So we learned about a prism, but here we can see a triangular prism. So let us see what is it. A triangular prism is a type of prism with 3 sides and 2 bases. The sides are of rectangle shape and bases are of triangle shape. Altogether, it has 5 faces, 9 edges, and 6 vertices. Now, how can we say that it has 5 faces, 9 edges, and 6 vertices? Again, we will see it how. Here you can see face number 1, face number 1. Here you can see the face number 2. Here comes the face number 3, face 4, and face 5. So now you can see that it has the 5 phases. We have proved it. Now let's come to the edges. Edges, I already told you that these are the sides. So again, we should see them. So how many edges? 1, 2, 3, 4, 5, 6, 7, 8, and 9. So these are the edges. Now what about the vertices? Again, simple. 1, 2, 3, 4, 5, and 6. So these were the faces, vertices, and edges of the triangular prism. So now can you think of a common or day-to-day life examples of a triangular prism? Well, let me tell you. If you have seen the camping tents, triangular roofs, and chocolate candy bars, they all are the examples of triangular prism. Well, it is very easy to remember them. These are the very common and day-to-day life examples. Now let us know about another figure, that is a rectangular pyramid. So again, before doing the introduction of this rectangular pyramid, I would like to introduce what is a pyramid. A pyramid is simply a three-dimensional structure encompassing its base with a polygon. So now what about this? This is a rectangular pyramid. So what is it? A rectangular pyramid is a three-dimensional object with a rectangle for a base and triangular face corresponding to each side of the base. The triangular faces which are not rectangular base are called the lateral faces and meet at a point called vertex or apex. So now, as similar to the cube, it also has the same dimensions, that is 6 faces, 12 edges, and 8 vertices. Again, we will be seeing it how. Here you can see the face number 1, the face number 2, the face number 3, face number 4, 5, and the base or the last one, 6. So here we conclude that it has the 6 faces. Now what about the edges? See, 12 edges as similar to the cube as I told you. 1, 2, 3, and 4, 5, 6, 7, 8, 9, 10, 11, and 12. So 12 edges, you all saw it. Now vertices. 8 vertices, how? See. 1, 2, 3, 4, 5, 6, 7, and 8. So this was all about from my side, and I hope you all might have understood. So from this activity, what do we conclude? We conclude that all these objects, whether it is a cube, a rectangular pyramid, or a triangular prism, from all these things, we conclude that these all are the 3D figures which have 3 dimensions, length, breadth, and height, and they have faces, edges, and vertices. And these can be easily found in our day-to-day life, and we can see them. Thank you.
It was an impressive presentation in 19. Now I call upon M21 for their activity.
A super evening to one and all present here. Today, me and my friend are going to explain the concept behind finding the total surface area of cylinder. So, and also the relation between faces, vertices, and edges. So let's begin.
So today we are going to explain the concept behind finding the total surface area of a cylinder. I have taken a cylinder. Now I am going to cut it and see which all shapes do I get from a cylinder. So let's start. First we will cut this. Now this. So we get a rectangle and two squares, two circles. So for finding the area of the cylinder, we need to first find the area of the rectangle, and then after that we need to find the area of both the circles and add all of them. Then we will find then the area will that area will be the area of a cylinder. So first we will find the area of rectangle, as the length is 15 and breadth is 10. So we will the formula of finding the area of a rectangle is length into breadth. So 15 into 10 is 150 centimeter square. Now finding the area of circle, the formula of finding the area of circle is pi r square, and we have two circles, so we will multiply the area by 2. 22 by 7 into as the diameter is 6, so we will divide it by 2 and get the radius as 3. So the radius will be 3 into 3, so we will get as 22 into 9 by 7, and the answer will be 28.28. And as I tell that we have two circles, so we will multiply the answer by 2, multiplied by 2. So the answer will be 56.56 centimeter square. And now we have to add both of them, 56.56 plus 150. So the area of the cylinder will be 206.56 centimeter square. Thank you.
Now we will explain the concept and the relation between faces, vertices, and edges. Now, if we add face and vertices, we will, if we add the faces and vertices, and there is a relation between faces, vertices, and edges. If we add face plus vertices and subtract it by the edges, we will get a special number, and that special number is 2. So let me clear. Suppose we will take cuboid. The faces that a cuboid contains are 6, and the vertices are 8, and the edges are 12. Now we will add face and vertices. By adding, we will get the answer as 14. Now edges are 12. We will subtract the sum of faces and vertices, and then we will get the answer as 2. Now we will see another example. of square pyramid, the faces that a square pyramid contains are 5. The vertices are again 5 and the edges are 8. Now we will add face and vertices. We will get the sum as 10. Now the edges are 8. Now we will subtract 10 from 8. We will get the answer as 2. And this is known as Euler's formula. Again, we will see example of triangular prism. The faces of triangular prism are 5, the vertices are 6, and the edges are 9. We will add the face and the vertices. We will get the sum as 11, and the edges are 9. So we will subtract 11 by 9, and we will get the answer as 2. Now we conclude that when we add face, vertices, and then we subtract it by edge, we will get a special number, and that special number is 2. This concept was given by Euler's formula. Thank you.
Well presented M21. Now I request M02 to make the performance. I repeat, I request M02 to present the performance.
Good evening, everyone. Today I am Anuj and I am Manoj of code M02 are going to perform an activity to on the topic 3D shapes. So my partner is going to give a brief explanation about 3D shapes. 3D shapes. These are also known as solid shapes. These have three axes, that is x-axis, y-axis, and z-axis. They have edges, vertices, and faces. Only the exception is sphere, which does not have edges or vertices, and it has only one face. Now I'm going to show you activity to prove the total surface area and the CSA of a cylinder. So I have a rectangle with length A, with length L, and breadth B. Now I will convert this into a cylinder. So as you can see, now this is cylinder. So as I have converted the length L into this circle, so we can say that now the L is equal to 2 pi r. That is the circle, that is the circumference of this circle. So the CSA is the circumference plus into the height of the cylinder, as it was L into B. So L is the circumference 2 pi r and the B is the height of the cylinder. So the CSA of the cylinder is 2 pi RH. And if we want to take out the TSA, then we just have to add the pi r square of the above circle and the pi r square of the below circle. Similarly, we can take out the total surface area of the cube by converting this net into this cube. The area of the square is a square, and this cube has 6 faces, means 6 square. So the total surface area of this cube will be 6a square. Thank you. Thank you.
Well tried, M02. Last but not the least, we have M04 with their activity.
A very pleasant evening to everyone. Today I, Mansi Verma,
And I, Aparna Shankar,
of school code M04 are here. As you all know that the relation between biology and mathematics has a lot of scope in coming future. So any link that connects to them becomes significant. Here's a question of biology which states that why are cells in an organism so small and not large in size? The answer to this question has as much to do with mathematics as biology, since it involves the basic concept of three-dimensional figures. We are going to explain you the relation between the ratios of surface areas and volumes of three-dimensional figures, especially here the cell as it increases in size. For that, let's imagine that the cell is a cube. Now let us move on to Aparna, who is going to demonstrate to us the relation between the ratios of surface areas and volumes through an activity.
Thank you, Mansi. Now, before we dive into the mathematical demonstration, let us first understand what a cell actually is. A cell is the basic structural and functional unit of life, and as you can see in this drawing, organisms can be broadly classified into unicellular and multicellular organisms. Unicellular organisms are made up of only one cell, whereas multicellular organisms have more than one cell. Us humans are classified into the category of multicellular organisms. But have you ever wondered the reason behind why cells are so small in size? This involves not only the concept of biology but also mathematics. Today, in this activity, we are going to demonstrate in front of you the mathematical explanation behind why cells are so small in size. For this, let us first assume the cells to be two cubes. Here we have a smaller cube which is of dimensions 5 into 5 into 5 and a larger cube of dimensions 7 into 7 into 7. Now, as we know, the TSA of a cube is 6 into the side square. Therefore, the TSA of the smaller cube becomes 6 into 5 square, which is 150 centimeters square. Similarly, the TSA of the larger cube becomes 6 into 7 square, which is 294 centimeters squared. The volume of a cube is side cube. Therefore, the volume of the smaller cube is 5 cube, that is 125 centimeter cube, and the volume of the larger cube is 343 centimeter cube. Now that we have found out the TSA and volumes, let us now find out the ratio of TSA to the volume. The ratio of the smaller cube becomes 150 is to 125, which on simplifying is 6 is to 5. The ratio of the larger cube becomes 294 is to 343, which on simplifying becomes 6 is to 7. 6 is to 5 is clearly larger than 6 is to 7. Therefore, it is evident that the smaller cube has larger surface area per unit volume ratio as compared to the larger cube. Now let us move on to Mansi, who will tell us some more interesting facts.
Now consider these cubes to be actual living cells which need oxygen and nutrients to survive and reproduce. For the entire cell to receive oxygen, oxygen diffuses through the cell membrane. Since the small cell has more surface area relative to its volume, every part of the cell can be supplied with oxygen quickly on comparison of the larger cell. If a large organism were made of a single cell, exchange of nutrients would not have taken fast enough. Since our bodies are made up of trillions of cells, it is necessary that the materials required by cells should be transported to the cell itself. This is why we have a circulatory system with a pump called the heart, which shifts the nutrients from the heart to the various cells. Now, Aparna will conclude this demonstration.
Did you all see how interesting the link between biology and mathematics is? In fact, this concept is not only used in biology but also in a field called nanotechnology. In nanotechnology, the increase in surface area per unit volume is exploited in rendering nanoparticles with special properties. For example, water filters use silver nanoparticles to provide cleaner drinking water to us. That was all for our demonstration. We really hope you enjoyed it. Thank you.
Good work, M04. What a wonderful performance by all the participants. The results would be sent to your respective schools. I thank Mr. Parnam Mukherjee and all teachers for the valuable time. Thank you and have a nice day ahead.